Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving examples for bending stress and bending moment of inertia in beams. The next example that we'll look at is a comprehensive example. We're asked to compute the peak normal stress in the beam due to the applied loading and indicate where it occurs. The section is a hollow rectangular section, and the beam is a simply supported beam with a series of point loads as shown. In order to solve this problem, we need to figure out where the maximum moment in the beam occurs, so we'll need to draw a shear and bending moment diagram. Then we'll need to compute the moment of inertia for the section and compute the peak stress at the top or the bottom of the section. We'll start by evaluating the shear and bending moment diagram. So first I note that I have a reaction. Beam develops a reaction, A sub y at support A and B sub y at support B. Because of the symmetry of the loading, the reactions are going to be equal and will both carry half of the total load of the beam. The total loading on the beam is 120 newtons, so each reaction is equal to 60 newtons. So now, extending down the lines for my shear force and bending moment diagram, extending the lines from each point of load discontinuity. I'm also going to create an axis to draw my shear force diagram, which I will label as V in newtons, and an axis for my bending moment diagram, which I'll label as M in Newton meters. Starting with the shear diagram, working from left to right, the shear force jumps up by 60 newtons at the end, is constant, then at the 40 newton load jumps down by 40, is constant, so the value here is 60. The value here is 60 minus 40, or 20. And it jumps down another 40 newtons to negative 20, and another 40 newtons to negative 60. And finally, at the end, it jumps back up by 60 to 0. The bending moment diagram, working from left to right, the moment starts at 0 at the left end, because it's a pin support. Because the shear is constant and positive, the moment is linear and increasing. The value at the first intersection point, 60 times 3, or 180. Then it's going to increase linearly again, but at a little lower slope. The value at the middle is 180 plus 20 times 3, or 240. And then it decreases down to 180 and comes back to 0, which we could easily check. But the symmetry of the moment diagram is in part due to the anti-symmetry of the shear diagram. So our maximum moment, note, occurs in the center of the beam, 240 Newton meters. Now let's evaluate the moment of inertia of the section. We can compute the moment of inertia for this hollow tube section as I outer, taking the outer dimensions of the rectangle as if it was a solid rectangle, minus I inner, where the inner part is the inner dimensions of the rectangle, or the hollow portion. So we're going to subtract away that portion. So the values are I outer, BH cubed over 12, B is equal to 40, the dimension in the Z direction, times the height, 26 cubed over 12, and then minus the inner rectangle. The inner dimensions are 37 for B, which is taken by subtracting 3 away from 40 for the two walls, each 1.5 millimeter thick. And the inner height is also 26 minus 3, or 23. Take that cubed divided by 12. The dimensions of the whole thing are millimeters to the fourth, and it computes to 21,072 millimeters to the fourth. Finally, we can evaluate the stress using the formula sigma equals my over I. Since I want the maximum stress, sigma max, I'll compute mc over I, where c is equal to the outer dimension from the neutral axis. I have a c bottom and a c top, which are both equal to half the height, or 13 millimeters. Okay, notice I'm dropping the sign on the stress equation, and that's because I'm going to compute the value and then deduce tension or compression by inspection at the end. And it's generally easier to do this. Okay, so let's plug in the values. For the moment, we said the maximum moment, 240 Newton meters at the beginning, at the midpoint. I'm going to convert that to Newton millimeters by multiplying by 10 to the third. So I have 240,000 Newton millimeters times my C value, 13 millimeters, divided by my I value, 21072 millimeters to the fourth, which gives me a value, computes to 148 newtons per millimeter squared, or megapascals, and that is the units in which I prefer the stress to be calculated. So that's the value. What about the sign? And also the second part of the problem asks, where in the beam does the maximum stress occur? We already said that it occurs at midpoint, because that's where the moment is maximized, and also will occur at the top and bottom of the section and be equal and opposite at those two locations because of the symmetry of the section. Since the bending moment is positive at that location, the beam is going to bend upward into a smile. We have compression at the top and tension at the bottom. And that completes this problem.